right, thank you everyone for joining Neural Magic session here with us today. I'm Gaurav Rao, I'm our Vice President of Product. I'm joined by my colleague, Benjamin Finneran. Ben, you wanna just give a quick update on who you are?
Hi, I'm Benjamin Finneran. I'm a machine learning engineer here at Neural Magic, and I'm building out a lot of our new products.
Fantastic. All right, thanks. So for today, we wanted to give everyone a brief overview on who we are, what we do. And today has been a little bit unique as we are going to be demoing a new piece of software that we are taking to market in early Q1 called Sparsify. So you'll have the opportunity to walk through a demo with us and ask some questions. So before we actually get started, we wanted to go through some quick housekeeping items. First and foremost, this video recording will be shared. So we are recording the session today. And for those that are not able to join, or if you wanted to share this with a colleague, the video recording should be available within 48 hours. And the second thing we'd like to bring up is Q&A. So we have a vibrant Q&A team here with us to help answer any questions you might have. Please don't hesitate to ask questions as you have them. You don't need to wait till the end. The chat function is there. And we even have some interactive polls throughout the session that we'd love to pull some feedback from all of you and learn a little bit more about what you're doing within the deep learning space. And in that regard, we like to kick these off with a question: where are all of you from? So to get familiar with the chat and sort of the polling technique, if you could kindly reply in the Q&A portion, which is, if you look at the bottom of the Zoom screen, you should see a button that says Q&A. If you click and open that, if you could please tell us where you are joining from today. We'd love to know. Hillsborough, Netherlands, New York City, Silicon Valley, Cambridge, more Netherlands, Canada, Toronto, thank you for joining. Washington, D.C., Sunnyvale, California. Hopefully Sunnyvale, I'm gonna make a dad joke. Hopefully Sunnyvale is actually sunny and not a foot of snow like we have here in Boston today. El Paso, Texas, and Bay Area, California. Fantastic. All right, well, thank you all for joining and taking the time with us today to learn a little bit more about neural magic. So, as I mentioned before, we're gonna walk through a couple of slides to give you a flavor of who we are, what we do, where we're focused, and why you should care about Sparsify. So first and foremost, Neural Magic was founded and birthed out of research at MIT. We are about a 25-person company to date. We are venture-backed, led by Comcast Ventures, Pillar, NEA, Andreessen Horowitz, and Amdocs. And as you can see on the left-hand side, bring a lot of different enterprise experience to what we're doing. And the what of what we are doing, we have introduced and taken to market a AI software accelerator. So what we've been focusing on is alleviating some of the cost pressures that hardware accelerators can bring by enabling flexible price performance on CPUs through an AI software runtime engine. We're alleviating some of the complexity that hardware accelerators within deep learning can impose, especially as you think about sort of how deployments have changed and sort of the full stack that's required to make a machine learning deployment pipeline successful. And we're alleviating some of this pain as a software accelerator by simply deploying the way you would any other software in your environment, right? Whether it's container-based, if you're managing through Kubernetes. Effectively, our goal is to easily plug into the CI/CD pipeline that you're already running with today. And lastly, as a software accelerator, we're hoping to reduce and relieve the burden that a hardware accelerator can impose, right? In terms of being able to have the ability to run larger inputs, multiple models, which you may not have the luxury to do as you try to completely utilize and saturate the infrastructure that your hardware accelerator is running with. So for example, with GPUs, with small limited cache sizes, customers often tell us they have to run very, very specific batch sizes or throughput workloads in order to fully saturate the GPU and fully utilize it, right? Versus actually having that be a requirement of the outcome or SLA that they care about. Where are we focused? So today, as an early stage startup, we've been focusing in the computer vision space, primarily classification, detection. We've added support for segmentation, specifically UNets. And as we talk about some of the ways we achieve acceleration on a CPU, you're going to hear and see that these algorithms are not just applicable to computer vision, but can actually transfer, and we should see speed up in other types of domains like NLP as an example. This is the first point in the conversation where we typically like to poll our users and get a little bit of a better understanding of the types of models you're working with today. So I'm gonna ask and poll a question here. You should see something pop up fairly shortly. Hopefully you see something now. And it's really to get a flavor of the types of deep learning models you're working with today in your own environments. It could be building, it could be training, it could be deploying, all of the above. And I see people are responding. We have quite a few people who have picked BERT at about 13%. 75, 76% of you are saying you're using ResNets. 37% are saying MobileNet. 38% are saying efficient nets. And we're seeing a lot of YOLO, which is fairly consistent from some of the market feedback as well as the engagements we have today. A cross section of folks who are using classification, known classification models, popular object detection models like YOLO and single stage detectors. And of course, as NLP has risen, due to speech to text to speech, conversational AI, we're seeing a large population also using BERT. Interestingly, no GPT users. So thank you for filling out that poll. So the next slide we like to often show is, you're hearing a little bit about who we are in terms of, how the company was formed, where we're focused, and how we're doing it is actually a combinatorial technique. So we have, when you think of achieving performance as part of your deployment, there's typically two aspects to achieving this. There's compute and there's memory, right? And what we're doing here at Neural Magic is we have proprietary techniques to reduce the amount of compute necessary to process a neural network. And we're doing this by taking advantage of some of the natural sparsity within the network and using different types of deep learning techniques that are known in the market, like pruning and quantization, to effectively reduce or compress these models, but do so in a way that can preserve accuracy, or at least give the end user the ability to customize and sort of make and understand the trade-offs that they're doing. And this is going to be a lot of the focus that you're going to see in the demo that Ben's going to walk you through. But reducing the amount of compute itself is not enough, right, in order to get speed up on a CPU, because what you've done is effectively transpose the compute bottleneck to a memory bottleneck, and you're going to incur all of the memory bottlenecks as you try to run these networks. So the second piece of where we're focused as a company is how do we accelerate some of these memory bound processes, right? How do we effectively run and execute the network in the CPU and utilizing some of the CPU hierarchy? So this combination of sort of sparse acceleration plus accelerating memory bound techniques is how we achieve significant speed up on a CPU. And you'll see some of this in the demo. So what does performance look like now that we've sort of claimed we're achieving speed up? Again, you'll see some of the benchmarking live, but on average, compared to a CPU, utilizing these sort of, I'll say, two techniques, both on sparsity and both on memory bound acceleration, we're seeing about 3 to 4x performance gains as measured in images per second compared to sort of CPU deployments running deep learning networks. And one of the value propositions that you can think about outside of just performance, as I mentioned earlier, is flexible price performance, right? Utilizing some of the CPU and CPU infrastructure you may already have, right, as part of fetching instructions back and forth between a hardware accelerator, right? For example, within a server environment. And in those scenarios, we're seeing almost a 50 to 60% price reduction in terms of cost per inference, right? So you can imagine sort of a scenario where even where GPUs aren't present, right, there's value in being able to run on a cheaper, more commodity piece of hardware. And even where we have hardware accelerators, right, we can significantly reduce the cost per inference, especially as we add scale, right, as you deploy over numbers of servers, right, or VMs. And then at a high level, what does the neural magic packaging look like? And what are the key components of our software accelerator offerings? So we have a model repo, which is effectively a set of pre-trained performance-tuned models that we've created ourselves that are ready for end users to start using, right? So these would be some of the common models that you saw as part of the poll, right? So the ResNets, the mobile nets, the SSDs, and what we've offered within this model repo are different flavors of these models. So we can offer the dense model, which is effectively what you would see from a open source repo. We offer a version of the model where we have tuned it for performance, but maintain baseline accuracy. So this is more for the end user who is accuracy sensitive, but would like to see what additional performance they can get by utilizing these proprietary techniques that we have. And then the third flavor or offering we have within the repo is a performance tuned model that maintains 1% of baseline accuracy, right? So this is really for the end user who's willing to tolerate a little bit of accuracy drop in favor of performance. And the idea here is, we want folks who have a variety of different skills to be able to readily use our software. And this is one way we can do that. And it nicely brings up the next key component of our software packaging, which is the ML tooling. We're going to spend more time on Sparsify, which we are just in the process of betaing and taking to market. But the idea here is once we have these models, we want to enable power users or novice users who are new to sort of these pruning and acceleration techniques to very quickly be able to create performance or accuracy tuned models that are ready to deploy on our inferencing engine. So you're going to see a little bit of this in the Sparsify beta that Ben is going to take you through. But think of this as the idea of taking the model repo and making it readily usable and preparing it for inference in our engine. And this is where you'd have the ability to run libraries and scripts for pruning, transfer learning, et cetera. And then finally, as you may be aware, given we're a runtime engine, when it actually comes times to deploying and predicting, we have the neural magic inference engine, which is where you actually achieve and realize sort of the performance speed up. So this is, and I know I'm moving a little quickly. I want to save as much time for Ben as possible. Why should you care about what we're doing with Sparsify? We're seeing a couple of different trends in the industry, and one of them is models are getting bigger, right? And we like to show this slide on GPT-3 because you can quickly realize with 175 billion parameters, what it's going to take to effectively use, right, and make deployable in an environment, right? It's going to take money to spend on training, lots of memory in terms of processing. And then even once you do this, think about the cycle, a model life cycle of training, deploying, retraining, et cetera, right? There has to be a more efficient way to start taking advantage of large models. And more importantly, what you'll hear from Ben and our team is a number of these parameters are, they're often, I'm sorry, a number of these networks are often over parameterized, right? So there may be ways to actually reduce some of these parameters intelligently to preserve accuracy as well as increase performance by compressing. And this is where you're going to see and what you're going to see in Sparsify. The challenge with this, however, is when you look at some of the available tooling in the market today, many of them are either in their infancy or they're very difficult to use, right? It requires fairly extensive knowledge and patience, right, to manually make and understand the trade-offs that are required, right, in pruning as an example, right? How do I understand what is possible based on my network in terms of speed up? How do I accurately measure my loss sensitivity and ensure that once I've pruned, I'm able to recover? So what we're starting to see is, there's a need to be able to use large models, and models are getting larger, and the techniques and the way people are doing it today are not making it simple enough for the average user or even power users to really gain the results, right? Or the outcome of what some of these techniques promise. And sort of that's where Sparsify is coming into play. And you're going to see a lot of this in the demo, but really Sparsify is our entry into the market to truly simplify, right, the achievement of performance in deep learning by taking advantage of some of these known techniques in the market that are today manual and iterative and very hard to understand sort of the trade-offs that are being made for some of the outcomes that you're trying to get, whether that's performance or recoverability. So rather than spend a lot of time talking to a slide, what I want to do is actually ask Ben to, take over on the screen here and walk you through Sparsify so you can get a sense of how we're analyzing it, how we apply sort of the different techniques for performance improvement, and then how this can plug back into your own existing workflow. All
Thanks.
right, Ben.
Let me get Sparsify pulled up. All right. Can you see it?
We can see it.
Perfect. So this is the homepage for Neural Magic Sparsify. And it's essentially tooling that allows you to understand your models better and create optimal pruning configurations to optimize and compress your models. Once you have a pre-trained model or a trained model that you're ready to optimize, you can start with a project, and you can pull up Sparsify as easy as launching a Jupyter notebook, just a single Python command from your terminal. Now, for each model, you want to start a new project. We take in models that are represented in ONNX, which is the universal neural network file format, and we offer simple tooling to make it easy to export your PyTorch and TensorFlow models into ONNX. So once we get set up with our model, we can give our project a name. I'm running a Resident 50 model through Sparsify as an example, since so many of you on the polling said you are comfortable with that model. And now the first thing we do in Sparsify is we run analysis on your model for two factors. The first is performance, which is how fast does your model actually run in CPU and how will this be affected at various levels of sparsity and pruning. The second is for loss, which is at various levels of sparsity and pruning, how much do we expect the bottom line, which is accuracy, to be affected. And using these two metrics that we measure, we're able to figure out and help you understand the optimal configuration that you may want to take when pruning your model. So the next step would be to run your analysis. I've already pre-ran analysis, which takes a couple of minutes depending on your model. So we'll skip to the next page. So once you run your analysis, you can then take a look at the two factors. The first is performance. And we can see that our Resident 50 model measured in on our baseline CPU implementation at 6.7 milliseconds per batch. But we think we can do better with pruning. So we display here the estimated performance speedup that you can get from pruning a model to a safe recoverability. Other key features about this page include being able to take a deep dive into your model and understanding what's taking time when running on CPU. The first is grouped layer summaries. So you can see here that convolutional layers in Resident 50, as expected, are taking the bulk of the compute time. You can look in flops as well, that they take almost all the compute. So if we're able to prune away heavily from these convolutional layers, we greatly reduce the compute needed to run this network. Even more, we can break this down by layer-wise and see specifically which layers in the network take more time or have more flops than others. The intuition here is that layers that take more time or have more flops, we want to hit harder with pruning and prune them to higher sparsities, because that'll have a better effect on the bottom line of runtime. The next page you can see here is the loss profile. These are the results from our loss sensitivity analysis. And what the loss sensitivity analysis looks at is the magnitudes of the parameters in the actual model. No data is needed. It's actually shown that looking at the magnitudes of parameters gives you better insight on the effect on loss that pruning will have than if you run through the data. Although we do offer a one-shot approach where you run your model through data and see how pruning may affect it to get an equivalent loss sensitivity. And you can use both to create a configuration using our tool. So what we're seeing in this chart is the pruning loss sensitivity for each layer in our resonant model. And what we're seeing here is that the initial layers have much higher sensitivity than the downstream layers. And this makes sense because at the beginning of your model, you'll be given a lot of real information about your data. And this is in pruning away this data may have a greater impact on these downstream layers that read in from these initial layers. So the higher the pruning sensitivity for a particular layer, the less you may want to prune it because it'll have a stronger effect on your accuracy. What we see at this last uptick here is the final fully connected layer, which will have a different pruning sensitivity than the convolutional layers. So what we can understand here is that layers with the lowest pruning sensitivity, but also that take the longest to run, are the layers we want to hit the most hard, and we can prune the other layers accordingly to that guideline. Finally, we show the parameter counts by layer, which also gives you an intuition, same as the loss sensitivity, about how much we can prune from the layer. The more parameterized the layer is, the more likely there's lots of weights lying around that aren't actually doing as much as you may think they are. So once we have a good understanding of the loss profile and the performance profile, we're ready to start optimizing our model. So we have an easy optimization flow where you can select what optimizations you want to apply. Right now we're doing pruning, but in our upcoming release, we'll be adding support for quantization, as well as transfer learning from sparse models. Next step is to tell Sparsify about how you train your model. This is important because the learning rate and epochs used to train your model will help you determine what learning rate and epochs you want to use in order to retrain your model to sparse levels. So we give that information, we're taken to the optimization page. And what we can see here is that Sparsify has already generated a suggested sparsity profile for your model. So each item on this graph represents the suggested sparsity that we want to prune our model to. And we can see that given this profile, the estimated speedup will be 1.67x on top of the baseline speedup we get from neural magic. We also see the compression that we get from pruning the model, which is an added benefit, which is that the model can be compressed to much smaller layers by having all those zeros in it, which might have benefits for edge applications if you're running on devices with lower total memory. Now, my second favorite feature in Sparsify, I'll tell you about the first later, is the slider that you can use to reset the total model sparsity. And Sparsify will generate an automatic pruning configuration based on what sparsity you want to target for your model. So if we want to target 89% sparsity, let's just say, and that will give us a 1.82x speed up, Sparsify generates an automatic configuration for how you want to prune your model. For more advanced users, we have a flow where you can set the sparsity at each individual layer and see how it would affect the speed up of the overall model. We also allow you to set the learning rate as well as the number of epochs. And what we have here is the automated suggested learning rate. But if you understand your model, you may be able to set your learning to what you want it to be. So now to my favorite feature is the part where we actually have to prune the model, export. So what we see here in the first text block is the automatically generated pruning configuration that works with our neural magic software. And the great thing about these files is that they can be stored in version control into your CI/CD pipeline, so that when you store them with your model and the models change over time, you're able to see how your pruning configuration may change or pull back pruning configurations to work with other models. It can be easily shared across your team. Next is we show our integration code for both PyTorch and TensorFlow. As you can see, it's only 2 actual lines of Python in order to integrate neural magic's pruning software or optimization software into your training flow. And this is what I'm really excited about, is how simple it plugs in to the training flows that you already have. I've worked with an engineer who was using a pretty complicated training flow, and I sent him just this optimization flow. And within 10 minutes, they were able to start pruning their model. And as an engineer, that's what really gets me excited about APIs, is the ease of use. Because up to this point, everything is automatically generated for you, even up to the point of integrating with your training flow. You just have to run it. And then you see we also have integrations with TensorFlow, and we'll be adding support for Keras soon as well. So the next screen we want to see is benchmarking, to see how the pruning configuration we may have done would affect actual speed. So first, we want to run a baseline inference benchmark on the neural magic inference engine with no optimization to see how it runs. And we'll run with all the cores available in the machine, which is 16, and we'll do a batch size of 16 as well. Yep. So while I'm running the benchmark, I just want to remind you that you feel free to ask any questions in the Q&A, and our team will be happy to answer them, and we'll be taking them all as a team at the end as well. So the other benchmarks we would want to run also, we want to run the benchmark of our prune model to see what the actual speed up is. And we also want to run against Onyx runtime, which is a baseline CPU implementation. Right, so our first benchmark finished, and we have our results. So we're going to run again with the pruning configuration we just created, which is 89% sparsity. And we're going to run it for the same core count and the same batch size to get a fair benchmark. So when we see the expected speed up for sparsity, we also might be curious what the expected speed up for quantization might be. And when we're talking about quantization, we're talking about going from 32 bits of precision to 8 bits. And that would have a theoretical speed up of 4x. And then we're able to get speed up on top of that by pruning those quantized models. So now we're going to run our baseline model against Onyx runtime, just to see how a baseline CPU implementation might perform. We have our benchmark here. So as we can see, our prune model by far outperforms our baseline neural magic engine, and it greatly outperforms the Onyx runtime implementation. And obviously for your model, how much you can prune, how much you want to prune, and how much speed up you get depends on a lot of things, from your model size to your model architecture. And then recoverability will depend also on your data. So that's the main flow for Sparsify. The final thing I wanted to share with everyone is just a separate benchmark of our sparse quantized models. I'm going to pull that up now. It's just in a Jupyter notebook. Okay, Gaurav, can you see it? Yep. And this is just benchmarking our a baseline Resonant 50 model against a sparse and 8 quantized Resonant 50 model to see what the runtimes would be. Again, we're at batch size 16 with running on only 8 cores this time. So the first thing we benchmark is against the baseline model, and then we benchmark against the quantized model, and we see a 5.66 times speed up. And this is more than we could get from pruning or quantization alone. So the combination of pruning and quantization is what really drives speed up here. And then the final thing we'll show is just how various parameters in your training in your inference flow might affect the speed up. So if we run on batch size 64, it might be a high throughput situation. We can see how the speed up would be affected. And then this is what one of the things I'm really excited about and what we're doing is that these sparse quantized models can get some really great speed ups and make it very practical to be using CPUs for inference instead of other specialized hardware. All right, and now we see we get an even greater speed at running at a higher batch size of 6.74 times. Great, so that's the end of our demo. Now we'll be taking questions, and I'll pull up the Sparsify page again in case anyone wanted to see a particular screen or flow.
And maybe one, and thank you, Ben, for that great demo. Maybe as people are thinking of questions, maybe this would be a great opportunity to do one more poll. Now that you've sort of seen um, our techniques in terms of simplifying pruning, as well as applying things like sparse quantization techniques to run um, deep learning networks on CPUs, let's see if other folks in the forum are either familiar with optimizing models or are, optimizing models. We'd love to get your input here. So hopefully you should see a poll coming up as you think through some questions. Okay, we're getting votes in. Okay, we got a majority of the votes in, and 32% of you are saying that you are not optimizing. They're either too difficult or time sensitive. 37% of you are saying you are using quantization, and 32% of you are saying you are using structured pruning today. And about 15% of you have said you are utilizing unstructured pruning today. Okay. And hopefully, maybe Ben, especially to the users who are saying, no optimization is too difficult or time sensitive, maybe you can just highlight a little bit of the ease of use, right, that we've tried to build into the product here.
Yeah, definitely. So right from the beginning, I want to highlight that even if you don't have your own training flow right now, we've completely created ease of use tooling for end-to-end machine learning training. So you could pull a model, an Onyx model, straight from our model repo that you can put right into Sparsify. You can fine tune this model with transfer learning using your own infrastructure or our transfer learning flows so that you have a model trained for your problem, and then you can put it into Sparsify for analysis. Sparsify, like I showed you, is completely automated if you want it to be, or if you're more of a power user or want to have more specific things in your model, there's lots of higher level features you can use as well. But going through this entire flow, we didn't have to change a single thing to get to our optimization page, get to the recommended speed up, which I think was at 82%, or I guess it was higher. We got 1.67% speed up, and then get to the export script, which plugs either directly into your training flow or our own ease of use training and optimization flows that all it takes would be your configuration file.
Mm-hmm. Great.
And given this, you're able to achieve the speedups you need or even solve problems that you weren't able to before.
Got it. Thank you, Ben. And there's a couple of questions in the chat, about different types of models that could be applied or used within this tooling environment. I think I saw a question on YOLO, on BERT. Can you talk or tell a little about, what type of models is this applicable to, and where and what, constraints there may be, if any?
Definitely. So especially in our tooling, we try to make it as general as possible. So if you're using standard PyTorch and TensorFlow libraries where the parameters are easily accessible, even if you're writing your own, you have your own model, maybe it's not supported on the engine, but you're interested in pruning it, that could definitely happen as long as the models are available in the normal list of parameters in the model. And then we can prune the underlying layers just using the same code. Additionally, if you're interested in using your own pruning configuration, maybe you're not interested in unstructured sparsity or the other sparsity we support like block or channel. It's very easy to implement your own sparsity modifier, your sparsity code, and integrate it directly into our flow. That in and of itself is very simple, and you can use the rest of our infrastructure to optimize your models.
Got it. And there's another question in the chat from Serena, and I think you actually just hinted on this earlier in the demo, but what are we thinking in terms of being able to apply quantization and transfer learning features within the tooling?
Definitely. So for PyTorch quantization aware training, that'll be available in our release that will be cutting very soon, and then definitely available in our larger public release. Transfer learning, we already have the abilities for that in our tooling, and it's on the roadmap in the next maybe month or so for support within Sparsify. But you can already use transfer learning within the neural magic tooling. It's very simple, and you can definitely reach out to the team if you have any questions about it.
Great. I'm looking in the chat here. Satish is asking, are we able to provide a layer by layer pruning output for YOLO v3 as an example?
Yes. So part of the training flows we offer, um, all of the training algorithms have logging for the layer by layer sparsities that they're pruning the models to, and this is printed out during training as well as after. And we have integration to make it easy to visualize your model sparsities, your layer by layer sparsities in TensorBoard or another visualization tool like that. And then if you wanted to put your YOLO model through Sparsify, you would definitely be able to and see the potential performance impact from pruning layer by layer sparsities with your YOLO model.
Mm-hmm. Great, thank you for the explanation. And then another question that I think is worth bringing up here too, does Sparsify pruning improve the GPU performance as well, or are you only targeting CPUs for performance?
So there's kind of two answers to this question. The first is that Sparsify was made as a tool to first do unstructured sparsity for support on the neural magic inference engine, which is targeted towards your commodity CPUs. But now modern GPUs are starting to have capabilities for some forms of structured sparsity as well. And the great thing about neural magic machine learning tooling is that it can prune in many different ways. For example, like the A100 GPUs, we're able to prune for the blocks that they require. So Sparsify pruning right now targeted towards CPU, but we may be adding backends for other execution environments. But the machine learning tooling can prune to many different ways.
Mm-hmm. Okay, great. I don't see any other questions in the chat at this time. Let me see. And if I can share the screen, I'll put up one more slide for resources for people that are interested.
Let me
Oh,
set.
actually, and there's one, actually, while I'm doing that, there's a couple more questions coming up. Is there a plan to open source? So I can answer this one. Yes, there is. So, as we are making a conscious effort as a company to meet developers where they work, we feel there's an opportunity to open source several components in the package that I had just shown you in the slides earlier. So, Sparsify, both, the tooling as well as Neural Magic ML, as well as our pre-trained sparse zoo of models would also be falling under the category of things that we would be open sourcing. And while we answer a couple more questions here, I just wanted to show this page for from a resource standpoint. If you have more questions and you think of more questions, or you want to learn more based on what you saw today, come check out our resource page. Check out our website. We have a number of positions that we are hiring for within the company, and also, as we look to open source our pieces of our components here, for early access or registration, please sign up. We want to make this as easy as possible for people to find, to download, and have early access to some of our software. And of course, if there are other questions that you would like answered, feel free to send us an email, and we're happy to interact and engage that way as well. So let me leave this up and see if there are any other questions in the chat. Holger, is activation sparsity in scope for the tool?
Yeah, 100% yes. We actually published a paper earlier in this year about activation sparsity, and the full implementation for that is available in our machine learning tooling.
Great. And Serena's asking, is the full model zoo list on the resource page? It will be. And in addition, we also have several blogs, Serena, that outline not only the models that we have, but some of the use cases that we support with those models and how you can get started. So we have a couple of minutes, 2 minutes left. Any other final questions that people might have based on what they saw or what they heard? Okay, well, we hope you enjoyed the live demo. So thank you, Ben, for taking us through Sparsify. It's very exciting, and based on the questionnaire and the polls, it sounds like this could be a very interesting area for folks on the call that have joined us today. Thank you for joining us from all across the world. We had different people from different parts of the U.S. and different countries. So it's fantastic to see interest, and we would love to stay engaged. So please reach out. Please come to some of these landing pages where you can get more information, product access, and of course, as I mentioned earlier, we're hiring for different positions. So we'd love to have you apply if you're interested. So thank you, everyone, and have a great day.